Anyone?
No.
Kind of. Might have been in physics too. Might have been. It kind of branches over math. So the first thing we're going to talk about is velocity. Velocity is an overarching word that basically stands for, the speed of something in a given direction. Today we're going to talk about velocity rotation-wise and linear. And we're going to split it apart and see if we can understand what the difference is between the two. So let's go through these awesome definitions and let's break down what they mean. So linear velocity is the rate at which an object moves or travels along a circular path in 1 unit of time. Linear velocity is measured in linear units like miles per hour. Here's my thought on this. We're talking about circles today. We're doing linear velocities going around a circle. So picture you're in the parking lot and you're doing circles in your car. Your linear velocity is the speed that your car spits out at you. Say it's 15 miles per hour. You're driving around a circle, you're going 15 miles per hour. That is your linear velocity as you go around. You're going 15 miles per hour. It doesn't matter how big the circle is or how small the circle is, you're going 15 miles per hour. Now the next one we're going to get to is angular velocity. That is the rate at which an object rotates or turns about a fixed point in 1 unit of time. Angular velocity is measured in angular units like revolutions per minute. Let's go back in your car. You're driving around the parking lot in circles going 15 miles per hour. Linear velocity, 15 miles per hour. Maybe you're doing one full lap, you might say, every 30 seconds. 1 lap per 30 seconds is your angular velocity. How long does it take you to get around? So linear velocity is the speed, that 15 miles per hour. Your angular velocity is how many times you can go around over a certain amount of time. That's the big difference between the two. If you still have questions about that, that's okay. We're going through a big example together to hopefully make it more sense. We're going to talk about an ant on a clock. Maybe he'll help you make sense. And if we get through all that, then we got to ask some more questions if it doesn't quite stick. Okay, so we have the world's worst carousel. It's got 2 horses on it. You know what I mean by a carousel? You kind of spin around. They're at the fair sometimes. I'm sure we all ride those every year. But we have a carousel with 2 horses on it. We have a white horse and a black horse. The white horse is near the edge. The black horse is near the center. So suppose there are 2 horses on a carousel that rotate twice a minute. So that means this carousel goes around every minute. It goes around 2 times. It could be, maybe it's really big. Maybe it's like a mile long. That'd be really fast. I'm assuming it's a kid one. It's going nice and slow. So we're saying this carousel twice every minute makes a full revolution. So 2 revolutions every minute. We could say 1 revolution per 30 seconds, but we were given this. All right, the black horse is 1 meter from the center. It doesn't matter, it's just close to the center. The white horse is 2 meters from the center. Once again, all I really care about, there's a black horse close to the center. There's a white horse far away from the center. Now, the first question is, which horse has a greater angular velocity? Now remember, angular velocity is how many rotations you can do over a given time. What does this problem set up as our angular velocity? Twice a minute.
Both of them?
So in 1 minute, how many times does the white horse go around? Twice. Okay. In that same minute, how many times does that black horse go around? Twice. So who's got the faster angular velocity?
None? It's the same?
Neither. They're both the same. I'm probably not going to write anything in here. This is for you to write stuff down to see if it makes sense to you. But they're both going 2 revolutions per minute.
I think the white one has...
We'll go to the next question in a second. So you write what you need to hear. I'm just going to write both are traveling at, what do we got? 2 rotations per minute. I'm going to put that as 2 revolutions per 1 minute. I'm going to start using our notation. I'm using 2 revolutions per 1 minute, which is 2 rotations per minute. I'm just going to write it as a fraction because fractions are going to be easier. In fact, anytime we talk about velocity, it's always a fraction. When you drive your car and you're going 15 miles per hour, that's 15 miles over 1 hour. It's a fraction. Whether you picture it as a fraction or not, it is a fraction. So they're both going the same angular velocity. Now, the difference is going to be how fast are they traveling using linear velocity? Which one's going faster in linear velocity? The black one or the white one? We're saying some white ones. I heard some black ones, white ones. Let's figure it out. Let's think this through. They're both rotating at the same speed, right? They're both taking, I have 1 minute to get 2 revolutions.
One's further distance.
One has to travel further distance in the same amount of time. Which one has to travel further?
White.
The white one has to travel further. So if I kind of mimic the white horse, we have to go all the way around here. And if I perfectly measure that out, the white horse has to travel that far. The black horse just has to go in that same amount of time. Well, it has to do twice. So my black horse in one rotation just has to go. So the white horse has to cover this in the same time, more ground. What do you have to do if you're covering more ground in the same amount of time? You have to be going faster. So which one has the faster linear velocity? The white horse. So when I think of linear velocity, even when it's going around a circle, I still think of a straight line. How far do they have to cover? How far do they have to cover? Is that good? Are we a little clearer on angular and linear velocity? Feeling okay with that? Now let's throw some equations at you so you can feel confused again for a second. Don't get bogged down in these equations. All right? These are really easy to do if you just break them down into one kind of thing. So we have linear velocity. Linear velocity can be calculated by distance over time. Why does S stand for distance? I don't know. Sometimes they do that. So we have distance over time. But for this class, this is going to be the big one we use. Velocity is going to equal r times omega. R stands for radius. Omega is going to stand for your angular velocity. In this class today, we're going to find angular velocity first, and we're going to turn it into linear velocity. So we're always going to have this one, which means we just need a radius, multiply it, and we have our linear velocity. So think about that. That's how easy linear velocity is going to be today. All you need is an angular velocity, and you just multiply it by a radius, and you have linear velocity. Now, we do have one caveat to that when we talk about angular velocity. Angular velocity can be linear velocity divided by radius, because I just manipulate kind of these formulas. But our big one we're going to use today is this one, where theta, that's my theta right there. Theta is going to be the angle of rotation in radians. I'm going to circle that word because we need to get that in radians and put it up there. For our horse example, did I say radians ever? No, that's revolutions. That's not radians. Radians must have pi in it. So if I'm doing 1 revolutions per minute, that's 2 pi per minute, because 1 revolution equals 2 pi, because 2 pi equals 360. All right, so our flow for today. We're basically going to be given, kind of like this horse, we're going to be giving our angular velocity somehow. They'll say like revolutions per minute. We're going to turn it into radians. We're going to then have our angular velocity. We're going to chuck that guy in there, multiply by our radius, and we'll have our linear velocity as well. That is the entire flow of today. So don't get bogged down with the equations and omegas and thetas. Just think, I'm going to be given revolutions. I'm going to turn those into radians. Sometimes it'll be given to you in radians, but if it's not, you turn it into radians, multiply by radius, and you now have your linear velocity. And if that's confusing, let's go through an example together. And this is going to be Adam the ant. This is one of 2 ants that will appear in our pre-calculus class. Just wait till you get to see Pierre. He's a mountain climbing ant. It's pretty cool. But this is Adam. Adam's on, not our clock, because our clock doesn't work. But say our clock worked. He's sitting on our second hand of the clock. He's 12 centimeters from the center. What is his angular velocity in revolutions per minute? So I said every one of these problems will at the very least give you your revolutions per minute. So we're going to get our angular velocity in revolutions per minute. And I'm going to go ahead and write that down real quick. So we have omega equals our angle, or how much ground we're covering, over our time. So that's our rotation. Yep, someone's getting there. So you might say it doesn't say anything about rotation, but it does, because it says it's on a second hand. Revolutions per time. How can I talk about the second hand in terms of revolutions per time? What was that? How long? It represents a minute. So we could talk about minutes. We can say something per 1 minute. How many revolutions does a second hand do per minute? 1 revolution per minute. It takes a minute to go around. 1 revolution per minute. So it did. A lot of the problems in the homework we'll straight up give it to you. It'll say RPMs or something. This one we had to delve in and get it. So this is my angular velocity in revolutions per minute. Now, if you remember that key thing, I'll come back to the slide for anyone I said it has to be in radians. So it's going to be let's do the actual work, because sometimes you won't just see it. It might be like 2.5 or it might be 2,500, and we got to figure out how to turn it into radians. This is how we're going to turn it into radians. So we're going to start with our revolutions per minute. So we're going to come down here, and we're going to say, okay, that was 1 revolution per 1 minute. Now we're going to do a unit conversion. We're going to do a unit conversion. I need to get rid of revolutions, and I need to change it to radians. So when I use unit conversions and I get rid of something, I'm going to put revolutions down there, because I can't use revolutions. I need radians. I need it to be like 4 pi radians per minute or something. So we have revolutions. How many revolutions are in 2 pi? 1. Are we settling on 1? Okay, it's just 1. So what we're going to do is we're going to have 2 pi. Now, normally you don't do this, but I'm going to put radians. You don't really need that. Most of the time that's gone. We'll just have 2 pi. But just for the sake of our notes, I'm going to have 2 pi radians per 1 revolution. That means our revolutions cancel out. And we now have 2 pi radians per 1 minute. I'm going to change this to just rads. Rad. It's pretty rad. Once again, you do not need those radians. We usually don't write those, because once you see the 2 pi, you're already like, oh, we're in radians, obviously. Are we good so far? I got a revolutions per minute. In short, pay attention to what happened next. All I did was I multiplied by 2 pi. That's all that happened. I multiplied by 2 pi. So I got my revolutions per minute multiplied by 2 pi, and now I have my angular velocity in radians. Now I said our next step was to turn it into linear velocity. So what is his linear velocity of centimeters per minute? So if we go back here, I said we're using this one. Velocity equals radius times our omega, which is, we already calculated that. So our next step is velocity. Wait, am I the wrong one? Yeah, thank you. We have velocity equals our radius times our angular velocity. Angular velocity is right above. It's that 2 pi. What's the radius of the circle that he's forming? It is 12 centimeters. If he's 12 centimeters from the center of that circle, and he spins around, he's always 12 centimeters away from it. That is your radius. So this is going to equal 12 centimeters. I'm going to put that over 1 for just a second, because we're using multiplication. You normally won't. And then we have 2 pi radians per 1 minute. It will be, yeah. I just want to stop here. This is for anyone that cares the nuts and bolts behind it. Most of you are like, who cares? We can do them all. You're like, we're already done, right? I want to show you some nuts and bolts and why I had radians in here the whole time. Units have to cancel out. We're not in a science class. I don't need to see your units cancel out every single time. But something interesting happens here. Since 12 centimeters equals 1 radius, you can actually put radius right here, which will actually cancel out the term radian, because we said a radian is equal to a radius. You take your radius, and it becomes your radian. So that's what happened to your radians. They don't just magically disappear. They actually get crossed out, and we're left with 24 pi centimeters per 1 minute. Now, I don't necessarily direct you to do this, but I'm going to have a hard time if speed limits had pi's on them. Like if it was like, you have to go 3 pi miles per hour or something. It's probably not going to be easy. So usually when we give it in linear velocity, we approximate it. So once again, if we're doing linear velocity, we usually approximate that to some decimal. So this would be a time where you take out your calculator and we type in 24 pi divided by 1. And correct me if I'm wrong, because I really quickly went through this. I came up with about 75.4. And we could put that as centimeters per minute. I'm going to round to the hundredths just because that's what my notes have. So I have 75.40. Does that make sense? That'd be 0.40?
Yeah.
Okay. In a nutshell, that's our entire lesson. That we just have to find our revolution. We're going to keep going just so we can clarify stuff, and we might go through an example. We're going to first do the unit circle, and then we'll go back and we can do the example together. All right, so we have 75.4. Okay, cool. Now the next thing says Adam crawls to a point 5 centimeters from the center. Now he's 5 centimeters from the center.
So it's the same thing, just change the 12 to a 5?
I changed the 12 to a 5 because what's his angular velocity now if he's 5 centimeters away from the circle?
It's the same.
How long does it take him to do one full revolution? Same, 1 minute, right? So the angular velocity needs to be the same. So his angular velocity is going to be exactly the same. And what did we come up with? We came up with 2 pi 20. We had 2 pi radians over 1 minute. We could put radians if you want to. So it is the exact same.
Is that always?
Yeah. No matter how far away you are from the center, as long as you're on the same object that's moving, your angular velocity needs to stay the same. Kind of like the horses on the carousel, whether you're the white horse or the black horse, that's the same. Your linear velocity should change though, right? So now I'm closer to the center. Should I be going faster or slower if I'm closer to the center?
Slower.
I should be going slower. So hypothetically, you can just kind of check your work and go, okay, it should be slower. Our velocity is going to be, our new radius is 5. Yes. Will be 5 centimeters per 1 radius. Remember, we don't need those rads. I'm just doing it so you can see them cancel out. We have 10 pi centimeters per 1 minute, which approximately is, correct me if I'm wrong, I came up with 31.42.
Yeah.
Then I have one more question. We're going to do the unit circle, and hopefully we'll have time to do the example, because the example we're going to do next has more unit conversions where you have to go from like feet to inches, hours to minutes, so we can see that done. But we got one more question before we get to any of that, and that is Adam crawls to the very center of the clock. Mine kind of looks like it's to the dock. But we're to the clock. What are his angular and linear velocity? Let's talk about his angular velocity. Does his angular velocity change now that he's at the very center of the clock? Here's my question. How long does it take him?
Or does he still have to move?
He still moves.
Oh.
He does this. How long does it take him to do a full revolution? What was that? 60 seconds, probably. So does his angular velocity change? No, his angular velocity is the same. So angular velocity is still the same. It's that 2 pi over 1. So that remains the same. What's his linear velocity?
0.
It is 0. And we can prove it's 0 because what's his radius? 0. What's 0 times anything? 0. So we can go linear velocity. Either you understand that he's not covering any ground, or you can go, oh, the radius is 0 because that's our new radius, times our angular velocity equals 0 centimeters per minute. Or you can just holistically know he's not covering any ground, it's 0. He's just spinning around in a circle. Good with that? Seems like you guys have seen this before. That's why I'm going to skip our example. We'll go back to it if we have time. But I do want to make sure that we have a basis for filling out our unit circle. You guys don't have these yet. I'll hand them out to you right now. Then we'll have 270. Then we'll have 300. And then we'll have 330. Nope, that says 333. Let's go 330. And then if you want to, you can put the 360. You don't need to. It shouldn't be hard to add 30, right? That's pretty quick.
Degrees is easy.
Degrees should be easy. We should just fire those through. I just want to make sure you get them correct, that you don't lose points for degrees. Degrees right here is half. In fact, I just think 15s. 30 plus 15 is 45. Then I go to the next one. 120 plus 15 is 135. Then you go to the 210 plus 15 is going to be 225. And finally, you go to 300 and you have 315. Now, like you said, degrees should be easy, but this can make it even easier, just a little quicker, that you're not taking time thinking about this stuff. So think 30s and 15s when you're doing degrees. It goes really, really quick then. Now let's do radians. Radians are not hard. They just involve you memorizing 3 numbers and a couple of rules. So first of all, you should know these key points that will help you fill these out. So in radians, you have 0, right? And let's say you haven't done this for a while. You might go all the way across. What goes all the way across? Pi. Then what goes straight up?
Pi over 2.
Pi over 2. This one's sometimes a tricky one. We have 3 pi over 2.
So no one is doing this on the same circle or different?
Same circle. Oh, you can do whatever. These are yours. There's 4 circles if you want to practice it, or I should have said that. Yeah. Take whatever notes you need to. Those are your 4 circles. I'm not checking even if you did it. If you want to look at it and not do anything, you can do that as well. All right. Radians can be really easy as long as you kind of just follow this rule. You have to know 3 numbers. Does anyone remember what? Yeah, I heard some numbers. We're getting there.
It's 3, 4, and 6.
3, 4, and 6 are the only 3 numbers you need to know. You just need to know 3, 4, and 6. Those are your denominators. And I'm going to start on quadrant 1 because this 2 tells you what to do. You can either count up going this direction or count down to 2. So this denominator is going to go 2, 3, 4, 6. So we're going to go 2, 3, 4, 6. And then we're going to go to the other side, which mirrors it. I'm going to count down as well. I'm going to go 2, 3, 4, 6. And what's going to happen down here? See this 2? It's going to go 2, 3, 4, 6. It's going to go 2, 3, 4, 6. You have all of your denominators correct now. So just use that 2 as a guide. So it's 2, 3, 4, 6. Other side, 3, 4, 6. Now every one of these will have pi in the numerator. So go ahead and add pi to every numerator. Give yourself some space because some of them have numbers in front of it. So I'm just going to put pi on the back half of my lines on every one of these.
On the top?
On the top, yep. So on the top of the 3, 4, and 5, and 6 on every single one of them. And if you're on your own, writing these really, really quick. 3, 4, 6, as long as you keep those numbers memorized. Now let's learn a couple rules, because normally we just memorize this. But if you know a couple rules, it's really, really easy. If you're in the first quadrant, your numerator is 1. First quadrant, numerator 1. And if you didn't know that, you might want to write that down. You might want to put numerator equals 1 if you want to use this as your notes. What was that?
You don't have to write.
You can. I'm not going to make you write anything in your notes.
No, I just mean like in the unit circle.
You can write it where, yeah, if I found the quiz, you're filling out a unit circle, you can put numerator equals 1 if that helps you write it on the test. All right. Then let's go to quadrant 2. Quadrant 2, I'm going to write numerator needs to be 1 less. I'm going to write numerator needs to be 1 less. And it's going to be 1 less than the denominator. So numerator needs to be 1 less than the denominator. So if I have pi over 3, 1 less than 3 is 2. So we're going to have 2 pi over 3. If your denominator is 4, you go 1 less, which would be 3 pi over 4. And if your denominator is 6, you're going to go 1 less, which is 5 pi over 6. Yeah?
Is it the first quadrant is always a 1?
First quadrant's always going to be 1. So if you wanted to add those in there, you could. You could put 1, 1, 1 if that helps you remember it. So if I'm writing my notes, I'm going to say first quadrant, numerator 1. Second quadrant, 1 less. I'll actually just write 1 less. Like if I'm on a test, I'll just put 1 less. Third quadrant is going to be 1 more. So second quadrant, 1 less. Third quadrant, 1 more. So if your denominator is 6, in the third quadrant, your numerator is going to be 7. If you have a denominator of 4, your numerator is going to be 5. 3 is going to be 4. That's pretty easy, right?
Yes.
That's stuff we could memorize. It's just little rules. So first quadrant's really easy. Second quadrant, easy. Third quadrant's really easy. Bless you. Fourth quadrant's a little more difficult because it's different. It's different. You can either memorize them. What I do is I multiply the denominator by 2 and subtract 1. Multiply the denominator by 2 and subtract 1. That's the easiest rule I can remember for that.
Denominator?
Denominator. So multiply your bottom number by 2 and subtract 1. Multiply your denominator by 2 and subtract 1. So for example, if my denominator is 3, multiply 3 by 2 and you have 6. Subtract 1 and you have 5. Denominator is 4. Multiply it by 2, you have 8. Subtract 1 and you have a 7. 6, you multiply by 2, you subtract 1 and you have 11. So realistically, your fourth quadrant is the only one you should really mess up because it's different. It's not like 1 less, 1 more, just 1. You actually have to do a little bit of work. All right, questions on that? We're good with that? Okay, cool. All right, I am going to go back to that example because I think we have time. What time are we done at? We are done at 55. Oh, yeah, we have 15 minutes. I forget that we have such long classes. Yeah. Yeah. Oh, yeah. Sorry. Yeah, 3 is going to be, let me pause this. the reason why I want to do this example is we get angular velocity and linear velocity, or at least most of us. You are presenting that you understand the material. The difference here, the difference here is we're going to have to do some unit conversions. All right, so let's go ahead and read this. So what are the angular velocities in radians per second? They're telling you exactly how it has to be radians over seconds. And a linear velocity in miles per hour to the nearest tenth of the trip of a 22-inch lawnmower blade that is rotating at 2,500 revolutions per minute. So they go ahead and give you the angular velocity, not in the correct form, because it asks it to be in radians, which we always have to do. Whether they ask for it or not, we're going to find it in radians, and we need it in radians per second. So let's look at what they gave us. They gave us our omega equals 2,500 revolutions. Revolutions per 1 minute. And they want it in both radians and seconds. Note it's in minutes and revolutions. So both of those things are wrong. So the first thing we're going to get rid of is the revolutions. An easy way to turn things into radians is just multiplying by 2 pi. I'm going to do the full thing, but you might want to just get in the habit of multiplying by 2 pi. It's easier, and you don't have all these fractions. But I'm going to multiply by 2 pi over 1 revolution. So my revolutions cancel out. And I'm now going to have 5,000 pi, basically radians. I'm going to leave off radians because I said we don't always need those, per minute. So I'm partway there. I have radians per minute, but I need radians per second. So this is where we have to do unit conversions and understand this is the easiest way to do them. I need to get rid of minutes. So I'm going to put a fraction that has minutes on top, because they need to be opposite. If one's on the bottom, to cross it out, you have to multiply by minutes on top. So that we could go ahead and, if need be, we could cross out minutes. Of course, I've done nothing. I need to see how do minutes compare to seconds. 60 seconds per minute. So what I'm going to do is I'm going to go, okay, in 1 minute is equal to 60 seconds. I think I went ahead and just approximated at this stage. Yeah, so this will be something, remember when you multiply fractions, you go straight across. So in my calculator, I would just do 5,000 pi times 1, which is just 5,000 pi. And then I'll divide 1 times 60, which equals 60. And if you plug that in your calculator, you should get out not an equal to, but an approximately 261.80. And that's going to be radians per second. If someone could double check my math, that would be great. It works? Cool. Thank you. All right, so that just made us do one extra step. Still the same. Still revolutions per time times 2 pi is radians. It just made us change our minutes to seconds. Okay. Then it asked for linear velocity. You know it wants linear velocity in miles per hour, so I'm going to do 2 steps. I'm going to find the linear velocity as given, and then I'll convert it to miles per hour. So linear velocity, if I know my angular velocity, how do I find my linear velocity? By the radius. I do want to take the time to show you my awesome drawing skills real quick. I'm going to show you what they mean by this saw blade. So if you turn your lawnmower upside down, it's got a blade in it. Yeah, it was all free-handed too. You can tell by my curves after it. All right, here's the bottom of your lawnmower. This is what they mean by a lawnmower blade. So they're saying this entire thing is 22 inches. What's the radius of that blade? 11. So our radius is going to be 11. So although they gave you a 22-inch lawnmower blade, that 22 inches is the circumference. So our radius is going to equal 11 inches. If you got that wrong on a test, I'd be cool with it because you don't know what it might be just one blade spinning around. If you're ever uncertain on a test of what I'm asking, just raise your hand and say, is this the, because if you ask me, is this the radius, I know you're looking for the right thing. Your thought process is correct. Okay, so we have 11 inches, so all we have to do is go, okay, our linear velocity is just going to equal that 11 inches times our angular velocity, which we said was 261.80. And we said that was in radians per second, which is going to ultimately give us, I have 2,879.8. Is it 80 or did I completely, what would it be to the hundredths? It'd be 7.9. Okay, I'm going to leave it in hundredths since I did the other one. Inches per second. Thank you very much. Okay, we're close. We have linear velocity, but we have inches per second. It asks for miles per hour, so I need to change inches to miles, and I need to change seconds to hours. They got canceled out with, I'm sorry, I write that on their side, but this is 1 inch per radius. So the radians actually get canceled out. It's a good question. I eventually stopped writing that because normally we don't write that. We just know it disappears there. Okay, so we need to convert to miles per hour. So I'm going to do this without putting any numbers on it first. That's my advice to you, is do it all without putting any numbers on it and then go from there. Oh, that's a great drawing. All right, so we're converting to miles per hour. So we started with 2,879. Was it 0.79? Is that what we said? Okay. 0.79, and we got to make sure we put our units inches per second. Let's handle the inches first. So we know the next thing has to have inches on the bottom. What's easy to convert inches into? Feet. So we'll go feet. And now in my head, this is what I'm thinking. I'm thinking, okay, that will cancel out inches. But I'm in feet, not miles yet. So on my next one, I have to put feet on the bottom. Can we go feet to miles? Yes. Okay, so we'll have miles on top. So pretend we did all that work, we'd have miles. Theoretically, we have miles. But I have seconds, right? So we need to get from seconds to hours. You can either go directly from seconds to hours. A lot of people tend to do seconds to minutes to hours. I don't care how you do it, but you need to realize, should seconds go on top or bottom in the next fraction if I want seconds to cancel out? It's going to go on the top. Up to you. Either you go seconds to hours or seconds to minutes. Whatever you're sure you know. I'm going to go seconds to minutes just because it makes me do one extra step, because why not? And then I'll put minutes on top here, and then we'll go minutes to hours. That way my minutes cancel out. My seconds would have canceled out. And I will now see that I'll be left with miles per hour theoretically, as long as I put all the numbers in correctly. If you're doing unit conversions and you struggle with it, this is the way I'd always do it. Don't worry about numbers. Just worry about how your conversions look and where your fractions look. All right, to finish this off, you would then go, okay, there are 12 inches in 1 foot. How many feet in a mile? Yeah, 5 tomatoes. If you ever forget how many feet are in a mile, just say the word 5 tomatoes, because it's 5,280. 5 tomatoes are in a mile. 5,280. 1 mile. 5 tomatoes. 5 tomatoes. 5 tomatoes. We have 60 seconds in a minute. And we have 60 minutes in an hour. The only thing you're going to mess up now is your calculator usage. You need to multiply everything on top. So you need to have 2,879 times 0.79 times 60 times 60 and divide that by 1 times 12 times 5,280. My advice is use parentheses in your calculator. Open a parenthesis.
Where you can just multiply the top and then multiply the bottom and then.
You could, yes. I'm just saying if you want to put it all in at once, you can multiply the top, then hit your division symbol, open parenthesis, and multiply the bottom. However you want to, it's awesome. Just make sure you put it in correctly and you get the right value. Mine's going to be a little bit off. Mine, I ended up with 163.6 because I didn't round to the hundredths. So if someone can correct me at what that should actually...
163.6.
0.58?
Wait, that's the answer in total. I got some number.
You got 6.2? Did anyone else get 6.2? We got a 5.8. You got a 6.2? You got a 6.5. So we're going to leave it with 163.6-ish. Make sure you plug it in correctly. It should be a route there. If you got there, it's probably just what you started with compared to someone else.